Hello and welcome to this recorded e-learning that explains how to read timing reports to obtain timing closure. This REL is going to introduce the timing analyzer and the reporting formats it uses. After completing this module, you'll be able to describe a flow for obtaining timing closure, interpret a timing report to determine the cause of timing errors you may have, and apply the timing analyzer report options to create a customized timing report. Well, this is the timing closure flow diagram. Pretty much describes how to gain timing closure. Now, we're not going to touch on many of these topics in this REL. This diagram shows you the things you must consider from the very beginning of the design process, which starts at 1, obviously, but the point of this module is about the use of timing reports to gain timing closure. In other words, what you learn from the timing report will help you diagnose your timing problems. But before you get caught up and all the possible things you can do to fix the timing problem, you first will have to learn about reading timing reports and what they're trying to tell you. But for right now, we wanted to discuss how all the timing solutions fit together with the use of timing reports in a recommended flow. The first thing you have to understand is what is a reasonable expectation of performance. This is strictly dependent on your chosen device family, and as you know, they are each different. Each has its own dedicated set of hardware resources, and each has slightly different performance. Well, when we talk about performance, we're really talking about how your internal logic maps to CLB resources, that is, LUTs and registers. For this sake of discussion, we're not concerned about block RAMs, DSP slices, or dedicated processors, or gigabit transceivers. We're talking about how you get your generic HDL code to map to LUTs and registers, and then use that logic to meet your system timing needs. To do that, you first have to choose an appropriate device family that can meet your performance needs. The next topic is planning a good pin layout. This will directly affect your input and output delays, so it's important to follow some of the guidelines. And we have an REL on pin assignments. HDL coding is perhaps the most important topic, and as you can see, it comes up very early in the design process, and that's at number 3. This implies that the more effort you put into building a better design will actually help you be successful much sooner rather than later. And worse, of course, is if you don't use good HDL coding techniques, a lot of designers will end up coming back and changing their HDL code after they've built the design and implemented the design and end up wasting a lot of time. Next, at number 4, is making appropriate timing constraints for your design. As you may or may not know, the implementation tools will use timing constraints to determine if you are happy with your results. So in effect, if you don't write timing constraints, you're telling the tools you don't care about the speed of your design. This means that writing effective timing constraints is pretty much always done by every user, even if the performance expectations are modest. Finally, before synthesizing, it is recommended you choose a design strategy and goal. This is an automatic way to guide the implementation tools and synthesis tools, that is the place and route tools and XST. This will enable algorithms and software operations that will help you meet your objective, whether that's timing or area. After considering all these first few steps, most customers would have a pretty good design that is not a waste of time to synthesize and implement, although many experienced customers might not wait this long, and in fact some will skip these steps. We're guiding you through this process in the most thorough way so that you understand our guidance correctly. The first yellow triangle you see here is guiding you to review your synthesis tool's timing estimates, and hopefully this will give you confidence that you can meet your system timing goals. If you are way off, then we recommend changing your code or at least changing your synthesis tool settings to hopefully generate a more useful netlist. Next, you implement your design and use the static timing analyzer utility to determine if you actually met your timing goals. Till this point, the only timing information you had was an estimate, since completing implementation is required to know the design's routing delays. This may then require you to make an HDL coding change. Now we're around number 9. And make a path-specific constraint. Evaluate the placement of your logic by changing your tool settings, or make a design change, such as replicating a piece of logic to reduce a net delay. But no matter what it is, if the timing analyzer tells you that you did not meet timing, you'll need to make a change. But if you met your timing, you're done, and now you can generate your bit stream for programming your FPGA and do other things for debugging your simulation. Sometimes to change the tool settings, designers will use Smart Explorer or Explore Ahead, a utility that is part of Plan Ahead, to generate different implementation results. If that still does not help to meet timing, then users can consider making area constraints with the Plan Ahead software. Plan Ahead makes it easy to evaluate the placement of your logic and find a better place and route solution. After that, another implementation can be completed, and if you still have not met timing, you can try running the tools differently. Your last option is to migrate to a faster speed grade, a larger device, or a faster device family, or, at the next step, re-architect your design. This might mean inserting additional pipeline stages or getting another designer to evaluate your HDL code and find out why you have too many logic levels in your timing critical path. So as you can see, this is rather methodical, but the key is that the sooner you evaluate your HDL code and optimize your design to use the FPGA dedicated hardware resources, the sooner your device will meet your timing. Timing reports are provided by the Timing Analyzer, and they help you determine why your constraints are failing, or more specifically, why some of your data paths are failing to meet your timing constraints. Timing reports contain a detailed path description. The implementation tools can create timing reports for post-map or post-place and route timing. The Timing Analyzer is a report generation utility. It doesn't manipulate the place and route solution or help you gain timing. All it does is describe the data paths and the logic that makes up your data paths. When coupled with your timing constraints, it helps you to categorize your paths so you can generate a time report that will help you understand your design's timing. Now we'll talk a bit more about the Timing Analyzer report options a little later on. To open up a Timing Analyzer report, expand the place and route and expand Generate Post Place and Route Static Timing. Then double-click Analyze Post Place and Route Static Timing. Likewise, to generate a post-map static timing report, you expand Map and expand Generate Post-Map Static Timing Report, and then double-click Analyze Post-Map Static Timing. The post-map static timing report is an estimate of your design's timing. It is generated before place and route so you can determine if your constraints are realistic. The delay paths reported contain the actual logic delays, but the net delays in the post-map static timing report are estimates. When the Timing Analyzer opens, you'll see the primary windows. On the left side of the GUI, there is a hierarchical browser which lists all of the associated timing constraints with your design. In this case, that is a pretty long list, but it will depend on how many constraints you have associated with your design. The offset in constraint near the bottom has a red check, and that denotes that the constraint has paths that failed to meet the constraint. By selecting that constraint, we can look at the setup paths and the hold paths for that offset in constraint. From that path detailed information, we can get a good idea why that path failed to meet its timing constraint. By selecting a timing constraint from the hierarchical browser, each constrained path is shown with the longest constrained path shown first. The most timing critical path is the longest constrained path. Normally, the default report format will only show the 3 longest paths, but this can be easily customized. As the user selects different constrained paths, the report text window will jump and show the exact path detail for the selected path. In this example, we see at the top of the report that the offset in constraint was 15 nanoseconds, that 16 paths were analyzed, and 7 timing errors were detected. Then we see a minimum allowable offset of 14.967 nanoseconds on our setup paths. We also see that we have very little slack in this case. If our slack was negative, we would know that our constraint was failing. Further down in the report text, we can see our source logic, that's a pin in this case, and the destination logic. The report also shows a complete hierarchical reference to each piece of logic along the delay path as well. This is called the physical resource or logical reference. It helps you focus on which components are used to create your data path. It can be cross-probed so that you can just go back to your synthesis tool and look at a schematic representation of the data path with just one click. At this point, it helps to understand the delay types that are associated with FPGAs. Knowing this helps us to understand the exact configuration of the hardware resource that is being used. Note that each delay type is highlighted in blue. If you click on each delay type, the delay type will be defined for you. This same delay type information can be found in the FPGA's timing model found underneath your device's user guide. As I mentioned a moment ago, cross-probing shows the placement or a schematic representation of the logic in your chosen delay path. Simply right-click on the delay path to see the options you see in this slide. Then select an FPGA editor view to see the actual place and routing used, or you can select a technology view to show the logical path through these components. The technology view is helpful for understanding what logical resources your HDL code is inferring. This is the best way to determine whether you have a coding style problem. Note that the technology view is available from your synthesis tool after synthesis, so there is no need to wait till after implementation to use this tool. Now, it's not often that users will want to enter the FPGA editor to verify what resources were used. If you have a long routing delay, the timing report will show the actual routing delay associated with it. The timing report structure contains the timing constraint associated and the number of paths that failed to meet your timing. Note that the number of paths is important for understanding whether or not your timing constraint may be too tight. If the number of paths that is failing is very large, then you'll have to make a design change. If the number is small, then you might be able to run the tools with different software options to meet your timing. The datasheet report will show your setup, hold, and clock to output times for each I/O pin. This is a very useful section that customers often review. They use it to do a final verification that all their IOB registers or I/O delays are all going to meet their setup and hold times with the physical system. The datasheet report can be found by scrolling down to the summary section at the end of the timing report. The timing summary will tell you the total number of timing errors for your design. This is the number of failing paths for the entire design. The timing score is different. It's the total number of picoseconds all of your constraints were missed. So if your timing score is 0, then you met your timing constraints. If it is small, then you're off by a little. If it is large, then you really need to evaluate how many paths are failing. Based upon how far each path is failing, you can determine which paths are most critical and have to be fixed or even recoded. Finally, we get a timing report description which gives you the command line structure for the timing analyzer to regenerate this timing report. The paths report will show the slowest paths for your constrained setup paths. It will also show the fastest paths for your constrained hold paths. As I mentioned, the report will default to showing you 3 most critical timing paths. The component switching limits check that the toggle rate and duty cycle are within limits of the timing specifications you made for your design. In this example, we've taken a timing report and highlighted the top of the report in a blue box. This shows you that over 7,000 paths were analyzed and that 1,234 endpoints were analyzed. Further down in the report, we see there are no timing errors and that the minimum period was 11.11 nanoseconds. This is found by subtracting the slack from the timing constraint requirement, or by adding the delay path, the data delay path, the clock path skew, and the clock uncertainty. Near the top of the path is the path and clock summary. The data path and clock path will be described in the path detail if the constraint is an offset in or out constraint. At the top of this section is the requirement, that is the constraint itself, the data path delay, clock path skew, and clock uncertainty. Beneath that is the jitter, total input jitter, discrete jitter, and phase error. Further down in the data path description, we see our source logic with a hierarchical reference. The source logic is always listed first. At the end of the data path is the final destination logic at the bottom. If the timing constraint had been an offset in or out, we would have also seen a description of the clock delay path. The data path description is the most critical information you're trying to resolve a timing issue, but in this case our constraint was met. Note that the location references are shown in the left-hand side. This can give you an idea if your placement was good. The delay types are shown in the middle column, in this case the TCKO, which is a clock to output time, and the TI low, which is a LUT delay, are shown. Just to the right of the delay type is the actual delay. You should note from this example that this data path has 4 logic levels. That is the number of TI low delay types, or LUTs, that are on this path. This report will also show you the actual net delays for each part of the route and the corresponding fan-out. In this example, the net that goes from the first register to the first LUT has a fan-out of 35. You should note that after implementation, the routing delay includes true timing information, so this timing information is guaranteed for worst-case operating conditions. If you know that your system is not going to be operating at worst-case conditions, then you have some built-in slack into your timing system. Worst-case operating conditions is for maximum temperature and minimum core voltage. One of the features of the timing analyzer is to be able to customize your timing report for better than worst-case operating conditions. Finally, at the very bottom of the report is the total delay, which is all your net and logic delays. This section also includes a percentage breakdown. In this case, the path is 26% logic and 74% routing. Typically, with Spartan 6 and Vertex 6 devices, the data path is usually around 40% logic and 60% routing. Usually this brings the question, why is this path so long? But the first question I would ask you is, did this path fail to meet your timing constraint? And the answer was yes, it met the constraint. Then you're done. You don't need to get bogged down in details when you look at the design timing summary and see all your constraints are met. You can estimate your design performance from the post-map static timing report. In this report, the logic delays are accurate, but the routing delays are estimated because placement has not been completed. Instead, the net delays are only estimated based on fanout. Similarly, designers can use their synthesis report to estimate timing, but synthesis tools use loading models to estimate the net delays. Synthesis tools have net delays that are typically fast by 25 to 35%. Likewise, the post-map static timing report is typically fast by 25 to 35% as well. The key is to still use these timing estimates to make sure you have a reasonable chance of getting your timing objectives met. If you're way off, then you can still fix your design before wasting too much time generating wasted implementations. So this will save you time and effort. There can be lots of different possible timing errors that can be detected by reading a timing report. Poor use of the architecture resources can be seen if you know which delay types to look for in your data path. This can be fixed by instantiating proper resources. Using incorrect HDL coding styles is often seen when users have too many levels of logic. Poor synthesis results can be seen when you have too many logic levels or have the wrong resources inferred on a data path. Incomplete timing constraints, such as not using the appropriate path-specific constraint, can lead to too many logic levels on a failing path as well. Poor logic placement can be seen from the location information shown in your data path as well. This can sometimes be resolved by enabling advanced implementation options. But the correct interpretation of the timing report information is your best means of understanding your timing errors and why your paths fail to meet timing. In this example, there is a simple data path. The path starts from a register denoted by the TCKO, which is your clocked output time on a CLB register. The path goes through 3 LUTs. Each of these is denoted by the TI low delay type, which is your LUT delay. Finally, the data path ends with the setup time on the last flip-flop. In this example, there are 3 logic levels. Note that the fanout associated with each net is small. You should also notice the logical references. This path was constrained to 3 nanoseconds and failed to meet your timing. You should note that it barely failed to meet your timing, however. Why did the path fail to meet timing? More importantly, what can you do to perhaps change this path so it will meet timing? Well, note that the logic and routing delay and the percentage breakdown for both logic and routing. In this case, there is very little logic and a big chunk of routing. At this point, you probably already noticed that there is one net delay that is about 1.5 nanoseconds. That should pop out at you because it is larger than all the other net delays. I would cross-probe and go see the routing used. This would help you understand why this route is so long. Since the fanout is low, the delay is not related to skew. What ended up happening was that the pin assignments for the source and destination were far apart, so this forced the tools to have a lengthy delay. But since pin assignments were fixed, this could not be changed. That limits what you could do to fix the issue and emphasizes the importance of making a good pin layout. What other possible solutions could you come up with? Well, you could argue that there is too many logic levels and that the coding style should be verified or the data path could be pipelined. These would all be valid solutions, but recall that you barely missed your timing. I think if you ran the tools with some advanced implementation options, you could save yourself that design work and meet your timing. When you have a data path that is suffering from poor placement, as in our last example, there are a number of possible solutions. The most effective option is to increase your place and route effort level and turn on the par extra effort level. You could also try running Smart Explorer, which is covered in the Advanced Implementation Options module. In this example, there are 3 logic levels. When you review the data path, you quickly see that the fanout of 187 on net 2 will jump right out at you. Likewise, when you look at the percentage of routing delay, it confirms that you might consider duplicating the source logic for that net. If duplicating logic is going to be possible, you'll have to recode your logic. This may not be easy, but it will depend on your design, and it will work. The next step will be to determine how many times you should replicate the source logic. To get this path under 3 nanoseconds, you'll have to reduce the delay by 0.77 nanoseconds. That means the net delay has to go from 2.5 nanoseconds to less than 1.7 nanoseconds. This will require the logic to be duplicated at least twice and maybe more. To verify this, review the destinations of the net. So in other words, cross-probe, go to the FPGA editor, and now actually look at where the logic is being placed. If they're across the die from each other, then replication will definitely help, because remember now, the tools will be able to move that logic closer to the source and destination. If the net to be duplicated is the output of a flip-flop, the solution is to duplicate the flip-flop. You could use manual duplication or the automatic logic duplication synthesis option. If you cannot do the manual duplication, you could enable your synthesis tool to try it. If the net is driven by combinatorial logic, locate the source of the net in your HDL code and consider duplicating the entire component. This will require more logic, but again, it will help you get timing closure. In this example, there are 6 levels of logic on a data path. The path is constrained to 3 nanoseconds. The delay is 3.048 nanoseconds. Immediately, you're probably thinking, wow, that's a lot of logic in series. You're also probably thinking that the HDL needs to be recoded, and perhaps pipeline stages need to be inserted. Those are good instincts. Realistically, what has happened is that the customer built a couple of components, and one of them did not have a registered output. So this data path evolved by accident. So the solution is to find the components and make sure that the output of the early component infers a registered output. In effect, this would build a pipeline stage and help meet your timing. The next thing to ask yourself is, how am I going to balance the pipeline data path? Well, these are correct instincts, and if balancing is necessary, you'll have to build that additional circuitry as well. So, how do you solve this problem? Well, besides the best solution I just discussed, there are a few other things to consider. The implementation tools cannot do much to improve the data path speed because there are too many logic levels. The netlist will have to be altered to reduce the amount of logic between the flops. It would be wise to check whether the path is a multi-cycle path. If the path has got a clock enable, then it may be over-constrained. If we modify the constraint to correspond with a multi-cycle path running at a slower effective rate, then we're going to have more flexibility, and we might meet our timing right off the bat without making a design change. Another option is to ensure that you use proper HDL coding styles on each component and that timing constraints were used during synthesis. You can consider using the retiming option during synthesis, which will migrate registers along the data path more evenly as well. But most customers will have little choice but to add a pipeline stage and recode their HDL. There are a number of different timing reports you can make. From the timing analyzer, you can select timing and run analysis to create a timing report using the currently defined options and constraints. From there, you can select from 4 different types of timing reports. The 4 reports include design timing constraints, auto-generated timing constraints, user-specified paths by defining endpoints, and user-specified paths by defining clock and I/O timing. Now, most customers will use the design timing constraints type of timing report. This report will evaluate each of your timing constraints' ability to meet your timing objectives, just like we have shown you in all of our examples so far, where we had timing constraints associated with the design. The Analyze Against the Design's Timing Constraints report compares your performance with those timing constraints associated with your design. This is the most commonly used report. The Analyze Against Auto-Generated Constraints determines the longest path in each clock domain. It's used with designs that have no timing constraints defined for the design. If a customer wanted to use this report, I would ask them why they are not already using timing constraints. They would be missing out on a powerful means to improve the design speed by not using timing constraints. In fact, even if the timing constraints were loose, it makes doing static timing analysis a lot easier. I can argue that every design should have some timing constraints associated with the design. They can just be very loose timing constraints. Then the next report is Analyze against user-specified paths by defining path endpoints. This allows you to create a custom timing report by selecting groups of sources and destination elements, usually flip-flops, pins, that sort of thing. Now this really is used by customers who say, look, I just want to verify that my timing from this source to this particular destination is no longer than I need it to be. To use this, you group your sources and group your destinations with the timing analyzer, and then you'll use this option to create a timing report. The last report we cover is the Analyze against user-specified paths by defining clock and I/O timing. This allows you to define a period and an offset constraint after implementation. Now this is used with the designs that have no timing constraints associated with the design. So again, I would not recommend the reports used because I think everyone should have some timing constraints defined for the design. So reports 2 and 4, as I covered, are designed for the case you have no timing constraints. And I would ask, why would you want to do that? You should have timing constraints associated with the design, even if they're loose. And in that case, then you can use reports number 1 or number 3, or the first and third options I mentioned. The Timing Constraint tab allows you to select from various report options. In this case, when you're choosing a timing report, you should select a timing constraint file to be referenced at the very top of this window. From here, you have 5 tabs to choose from report options that are included. These tabs include timing constraints, report options, device settings, filter by net, and path tracing. Now the timing constraint tab options allow you to deactivate the reporting of a timing constraint. Note that this does not change the use of the timing constraint during implementation. Implementation has already been done. We are in the timing analyzer, so we're not changing the place and route solution. We're just choosing a report timing information that we want to read. In this case, the benefit is that we can reduce the size of the timing report. It's very common to use this option to report only the constraints that are failing. The Report Options tab allows you to do an unconstrained analysis. It also allows you to list some or all the unconstrained paths in your design. Your timing report also has the ability to show unconstrained paths. They are shown in a special section at the end of the report. This is sometimes used as a sanity check by the designer. You can also report only failing timing paths. This allows you to reduce the number of paths reported, allowing you to focus on just those failing paths. The tab also allows you to generate additional report sections. At the very bottom, we can see a data sheet, a time group section, and a separate constraints interaction report. The constraint interaction report allows you to determine which paths are being constrained by more than one timing constraint at the same level. Likewise, the time group section allows you to verify the components that are part of each group. The datasheet section at the end of the report will contain your design summary and the I/O timing on a pin-by-pin basis. Finally, the constraint details allows you to specify the number of detailed paths reported per timing constraint. You can see this option defaults to 3, but it can be increased easily right here. Likewise, we could also select to report only failing paths or report all paths. The Device Settings tab allows you to modify the speed grade. This allows you to determine if going to a different speed grade will help you meet your timing objectives. For example, if you are barely missing your timing constraints, you could use this option to quickly verify that using a faster speed grade will resolve your timing issues. All you have to do is select a different speed grade and regenerate the timing report. I recommend that if you use this, that you print out the entire timing report and staple the pages together and write on the front of the speed grade of the device that you've chosen. This just allows you to modify the speed file numbers associated with your silicon and save you from re-implementing the design. But since the timing reports often look very similar, it's important for you to denote in bold there what speed grade you're using, so any of your coworkers who look at this timing report will know what they're actually looking at. Prorating your timing report allows you to choose different operating conditions. That means you're allowed to modify your worst-case operating conditions. Remember that the tools assume your worst-case operating conditions by default. If you plan on operating in worst-case conditions that are better than a maximum of 100 degrees Celsius or whatever it is for your device, then this option will help you do just that. Likewise, if you plan on using a higher minimum core voltage, then you can change that here as well. Now don't forget, this is used only for what-if analysis. This will only allow you to determine how much slack you have. The Filter Paths by Net option restricts which paths are reported by allowing you to select specific nets with this GUI. Each net can be disabled or enabled by the user. Disabling any net excludes paths containing that net from being analyzed in a timing report or being reported. All nets are included by default with the design, with the timing report options as you see here. The Path Tracing tab enables or disables certain propagation paths from being reported. If a register is enabled, the path from an asynchronous clear port to a flip-flop to the output is considered a combinatorial path, and this describes the asserting edge. It's a reporting mechanism that enables you to display different types of delay paths so you can understand which paths are helping you fail to meet timing. Now let's wrap up this module with a brief summary. Timing reports enable you to determine how, and most importantly, why constraints were not met by analyzing and understanding the actual delay paths that were constrained. You can use the synthesis report or your post-map stack timing report to estimate performance before running place and route. And in these reports, the logic delays are known and accurate. However, the routing delays are not known, so they are estimated. The detailed path description offers clues to the cause of timing failures, and often by inferring information from those detailed delay paths, we can understand what might be the problem with the delay path and why it's failing, whether that's too many logic levels, fan out of net, placement, whatever. The cross-probe option allows you to see the placement of your logic on the die by going to the FPGA editor. The cross-probe mechanism also offers a technology view of a timing path, much like your synthesis tool provides a schematic representation of the logic along your path. Most people are looking at their technology view from the synthesis tool, but you can also do that here. That seems to help people the most by understanding their coding implications and being able to quickly reference the HDL code that's generating their logic. The timing analyzer can generate various types of reports for specific circumstances.